In a world where gravity is taken for granted, we decided to unravel the hidden truths that lie behind the scenes. Get ready for us to delve into the mysteries that defy our understanding. What if the essence of gravity, as we know it, is nothing but an illusion? Today, we will dare to challenge everything you think is true. Together, we'll penetrate the veils of perception and uncover the mysterious secrets hidden at the very core of the fundamental principles of gravity. We owe our understanding of gravity as a force of attraction to Sir Isaac Newton. In the 17th century, according to a very popular legend, Newton was watching an apple fall in an orchard. He noticed the apple fell exclusively downward, as if under the influence of a certain force, which inspired him to create the universal law of gravitation. What does this law describe? A conventional apple gains speed as it falls. The apple, like everything else on the planet, has a mass, but it's much less than the mass of the Earth. According to Newton, the force of attraction between the Earth and the apple directly depends on their masses, and is inversely proportional to the square of the distance between them. To make it even shorter, all objects with mass and energy are attracted to each other, and are in a state of free fall in relation to more massive bodies. This is all expressed in a well-known formula. The formula is broken down as gravitational force equals the mass of the primary, mass of the secondary divided by the orbital radius squared. By the way, Newton tried to model gravity as a field that surrounds all material bodies. This mental model is still used to explain the gravitational interaction between all objects. According to Newton's third law of motion, the Earth should also move toward the apple, since it also has its own field. But it's very small, and we cannot feel it, which can be explained by Newton's second law, F equals m times a. Since it's impossible to get the same acceleration for objects with different masses, even with the same applied force. However, it was not all bad news. Newton suggested that gravitational force may also affect space bodies, including the Moon. In addition, the satellite has not yet fallen to the Earth's surface, not only because of its constant rapid orbital motion, but also because of the gravitational interaction, which is less, between massive objects located at a considerable distance from each other. Newton was able to explain the dependence of the planet's rotation around the Sun due to the gravitational force between them with an imaginary experiment. If you put a cannon on a mountain and shoot a cannonball horizontally, it will fall vertically to the Earth after flying a short distance. But if you shoot it with a very high force, for example, up to 4,500 miles per hour, the cannonball will always be in a state of free fall and will not reach the surface. According to Isaac Newton, this is the state in which our Moon and, in particular, all other planets, even outside the solar system, are located. This is how Newton came to the conclusion that gravity is a universal force for the entire universe, acting in the same way everywhere. Moreover, Newton's law did not contradict, but complemented other relevant laws. For example, the three laws developed by Johannes Kepler, and they explained the movement of planets in outer space. The law of gravitation can be derived from each of Kepler's laws. Thus, according to Kepler's first and second laws, the orbit of each planet around a star is an ellipse, which means the distance from the planet to the star is constantly changing, including at the closest point from the planet to the Earth, perihelion, and the farthest point, aphelion, where the planet travels the same distance in the same time. Newton's law describes the acceleration of massive objects with respect to the distance to the star. In particular, the third law, which explains that an increase in the orbital radius affects the period of rotation, also explained in the same way. Moreover, the force that keeps the planets in orbit is proportional to the product of the masses of the Sun and the planet, and inversely proportional to the square of the distance between the two space bodies, just as it is between objects on Earth. However, Newton's law could not explain several important scientific observations. For example, Newton's theory explained the motion of the planets around the Sun well, except for one, Mercury. You may remember that Mercury has a strange oval orbit, but that's not the strangest thing. Its closest point of convergence is always in different places and moves slowly around the Sun. This process is called precession. Although this phenomenon is characteristic of all planetary orbits, it's most obvious and surprising in Mercury. The precession of Mercury's orbit is 5,600 angular seconds per 100 years, when observed from Earth. But the actual precession time of the planet is 5,557 seconds. Now, those lost 43 seconds cannot be explained by Newton's theory. However, all of this and much more can be confirmed by another theory, that is, considered fundamental to modern science, Albert Einstein's general relativity. Almost 300 years after Newton's revolutionary discovery, Einstein introduced the world to his view of the concept of gravity in the general theory of relativity. GR was preceded by the special theory, in which Einstein described that space and time should be perceived as an inseparable phenomena, such as absolutely everything in the universe moves simultaneously in time and space. According to GR, he explained that massive objects are capable of curving time, and thus affecting other objects around them, and this curvature is gravity. While Newton's theory was based on a falling apple, Einstein imagined a person in a falling elevator to explain his idea. Ash falls, he doesn't feel his weight because both his body and the elevator are falling at the same speed. However, when the person is moving up in the elevator, he feels accelerated, and it seems that the floors are resting on him. However, if there are no windows in the elevator, then the person will not be able to tell what he or she is experiencing from his or her point of reference. Falling in a gravitational field are moving at a constant speed in a small region of time. In Einstein's theory, this is called the principle of equivalence. In fact, if, according to Newton's law, a person falls down due to gravitational force, then, according to Einstein's theory, it's due to the absence of a force that pushed the person up. That is, a person is affected by the force generated by the elevator floor, but it is not gravity. This also implies that we are always in a state of acceleration, unless we're in a state of free fall or inertial motion from our point of reference. So then, Einstein concluded that gravity and acceleration are one and the same, and therefore, we're in a state of free fall until an obstacle appears in our path, which became the basis for understanding that gravity is not a force. This is a very unexpected statement. Let's take a closer look at the theory of relativity. So, as we've already noted, according to Einstein, gravity is a geometric curvature of a four-dimensional time-space. Its property is not a force acting in space. One can simplistically try to imagine time as a two-dimensional drawn fabric in which massive objects, like the planet and sun, create funnels, but this is not quite the right idea. A better option is to imagine time as a three-dimensional grid consisting of lines geodesics along which planets move in free fall. They are massive enough to distort the lines along which any objects move. That is why it may seem to us that, for example, cosmic bodies are attracted to each other. The theoretical physicist John Wheeler explained this idea quite simply. Space-time tells matter how to move. Matter tells space-time how to curve. We can't see the curvature directly, but we can see the effect of Einstein's gravity. For example, if the crew on the ISS is flying right next to the Earth, they will move in a circle due to the curvature. Although from their perspective, it will seem they are moving straight, but a large object prevents them from moving in lines. Furthermore, we can observe this on Earth. If two people move from a considerable distance to the North Pole, they will meet as they approach it. No force would act on them. They would simply follow curved lines due to the sphericity of the Earth. Same is true for light. Newton assumed that light is also bent by the gravitational force of massive bodies, like all other objects. So the actual location of a light source, like a star, is different from what we see. However, modern science knows that light has no mass, So how could it be affected by large cosmic bodies? Einstein, in turn, expanded that light, like you and I, moves along the same lines of geodesy. Since, according to GR, the lines around heavy objects are deformed. Light changes its course, meaning gravity does not act on the light itself. However, Einstein's calculations proved that the angle of light deflection was almost twice as large as, according to Newton. Einstein's idea was confirmed by astronomers Arthur Eddington and Charles Davidson while observing a solar eclipse in 1919. They compared the actual location of the stars with the light captured in the photographs and were able to confirm that the angular deviation is indeed approximately 1.75 angular seconds, as calculated by Albert Einstein. In particular, GR can also answer the question about the strange orbit of Mercury, since according to its calculations, the planet's orbit is shifted by 43 angular seconds due to the curvature of space. In addition, another proof that gravity is a curvature of time is that a wave of light can lengthen and lose its intensity due to the influence of massive bodies. So if an observer is in an accelerating spacecraft, then in his eyes, the wave of light emitted from the bottom point would be elongated relative to its original wavelength. This, in turn, would cause the color of the light to change from red to blue. This phenomenon is called the red shift of light and is not predicted by Newtonian gravity. In 2016, Professor Andrea Ghez led a team of researchers to observe the blue star SO2, which came close to the black hole. Sagittarius, if Finstein's theory is correct, then the light wave from the star should have changed its color to red for the scientist's reference point, and the star did indeed glow red, which again confirmed Einstein's gravity. So, Einstein's gravity model has made a real breakthrough in understanding the physical processes taking place in our universe. At present, it is confirmed by perhaps not all tests of its reliability and reveals many details of time, space. Nevertheless, the Newtonian model can still be a serious competitor for GR. While observing the rotation of disk galaxies in the 1930s, Danish astronomer Jan Oort first noticed that the rotation speed of stars on the edge of such galaxies remains constant, although they should be moving much slower. The solution to this paradox is the hypothetical dark matter, first described by astronomer Fritz Zwicky, which surrounds galaxies. According to current estimates, about 70% of the universe consists of 27% dark matter and 5% ordinary matter. However, although dark matter is an important hypothesis for explaining this phenomenon, in many others, such as bullet clusters, its existence has not been precisely confirmed so far. On the other hand, a modified model of Newtonian gravity, modified Newton dynamics, proposed by astrophysicist Mordecai Milgram, can explain the orbital rotation state. There are other rules for objects with much lower acceleration than in our system. Milgram modified the formula of gravity by adding the constant AO, which defines the critical point for acceleration. So, if the acceleration caused by gravity reaches this point, then Newton's laws, which were in effect before the critical moment, will be replaced by the new laws introduced by GR, and the inverse square law that we observe in our solar system would stop working, which will equalize the acceleration, meaning it will not depend on the distance from the center. This theory, in fact, explains the motion of stars and many other galaxies without the presence of dark matter. However, it has several serious problems. For example, it cannot completely exclude the presence of dark particles, since galaxy clusters and the Mond analysis are still characterized by the problem of insufficient mass, which is solved by dark matter. Therefore, this theory, although it offers an explanation for the orbital velocity phenomenon, has particular drawbacks that are still being solved by GR. Finally, the main problem with Einstein's gravity is the inconsistency with quantum mechanics. The main problem between these fields of physics is that GR is based on the principle of causality, while quantum physics is based on probability. Therefore, GR cannot work at the level of quanta, and quantum mechanics cannot work at the level of macroscopic objects. Since an observer will know where a large physical object is located and how fast it's moving, there's no superposition state for it. The only solution to this problem can only be to develop a new theory of quantum gravity that would explain the interaction of objects and fundamental particles simultaneously. Despite some problematic issues, Einstein's repeatedly confirmed gravitational model is still the basis for modern research, regardless of its age. We cannot say whether GR will suffer the same fate as the law of gravity, but the coordination of the model of the world according to the theory, along with other areas of physics, is necessary, without understatement, for the whole of science. So, since we do not yet have a new gravitational theory, we can summarize with some confidence that gravity is not a force.